All right, I think we are good.
Yeah. So today I will be presenting the CVPR 2022 paper, what makes transfer learning work for medical images, feature reuse, and other factors. So transfer learning is not a new concept. We have been it has been there from the AlexNet paper, and it has been used in multiple domains, including medical domains and in multiple tasks. So I'll give a brief introduction on this transfer learning quickly and move on to the details of this paper. Yeah. So transfer learning is like reusing the knowledge gained in source domain and using that knowledge to improve the performance in a target domain. So what we usually do is we train a model on a source domain, like a large data set, like ImageNet domain. And then we try to fine tune, like take the pre-trained model and fine tune it on a target domain, like maybe medical images or any other images that are relevant for the particular task. So that is what happens in transfer learning. And why do we do transfer learning is like it's based on a basic assumption that we assume that the features learned in the source domain will be helpful, will be useful in the target domain. So that is the basic assumption why we use transfer learning. Yeah. So in medical images, the transfer learning is quite popular. The reason is the medical images are like small in data size. This could be due to the rareness of the disease or the ethical concerns, or it could be due to the expense of acquisition. So since the data set in the target or the medical images is like small, what we usually do is we train a model on ImageNet. Like ImageNet, we have like 1.2 million images. So we train a model on ImageNet and we try to fine tune it on a medical image. And in medical domain, the image size, the data size could be like 5,000 to some hundred of thousands. But in the source domain, like ImageNet, like images, like there is 1.2 million images. So that is why this transfer learning is quite popular in medical domain. But there is a like clear distinction between the source domain and target domain, right? Because like from now onwards, the source domain is always ImageNet and the target domain is like always medical images. So when you consider the ImageNet, the images are like a clear global subject, and those are like the natural images. So in this image, you can see like, yeah, there are like spiders, penguins, like the clear global subject is there. But when it comes to medical images, it's different because there are large image of bodily region, and we use the variation in the local texture to identify pathologies. For example, in this X-ray, we use, there is not like a global subject, but we use the color difference or the texture difference between these regions to do the classification or detection. So there is a clear distinction between source and target domain. And also in terms of the image size, because in ImageNet, the image size is like medium size, it's like 224 into 224. But in target domain medical images, the images are like clearly high resolution images because we have to do detections, like to do disease predictions and so on. So the resolution is different and the image size is different, and also the number of classes are also different because ImageNet, we know there are 1,000 classes, but when it comes to medical image, the number of classes, it's definitely not 1,000, it's less than 100 maybe. And in some cases, just prediction of cancerous or non-cancerous. So there are like clear difference between target and source domain, like the ImageNet and medical domain. But how or why this transfer learning is working on medical images very well? Usually what we use is like train the model on ImageNet data set. There is, I don't think there are any other big data set which use particularly for medical domain. Haven't seen that. The de facto method is like trained on ImageNet and use that pre-trained weights on the medical image datasets. So why transfer learning is working for medical images? That's the question answered in this paper. So here I have summarized the contribution of this paper. So it shows that the benefit of transfer learning increases with reduced data size, smaller distance between source and target domain, model with fewer inductive bias, model with more capacity. And also the paper shows that the benefit of transfer learning correlates with feature reuse. Also the paper shows that there are benefits, there are feature independent benefits of pre-training, like speed up the training.
What is feature reuse?
Feature reuse, like we expect that the features learned in the ImageNet, like the edges, like the edges or the some other features like gradients are like directly used in the medical domain. That is the expectation why we use transfer learning, because we expect the features being reused. But one of the related work, which was published in NeurIPS 2019, they claim that there is no feature reuse, but the transfer learning only benefit due to the over parameterization and weight statistics. So by weight statistics, what they mean is like they take the mean and standard deviation of the ImageNet pre-trained weights and like initialize a normal distribution using that mean and standard deviation, and they sample the weights from that normal distribution. So that is weight statistics. And this paper, in the NeurIPS 2019 paper, they have used the weight statistics and showed that feature reuse is not important, but weight statistic is sufficient enough to like improve the performance using transfer learning.
That means like you start with the ImageNet pre-trained network and then you sample, use that network as a parameters.
Yes, to get the mean and standard deviation. Yeah.
And initialize the model from that.
Yes, exactly. Yeah.
That works better than using.
Yeah, the transfer learning. Yeah. That is this related work, the transfusion understanding the transfer learning for medical imaging. So this paper is about that. But here you can see they have only used two data sets. One is the CHEXpert, that is a chest X-ray data set. The other one is a private large data set again, it's a retinal fundus. So here the both data sets are like comparatively large, and they have used architectures like ResNet and Inception. So ResNet and Inception both are CNN based architecture. So in this work, what they have considered is really an isolated case, because they are only using the large data set and CNN based architecture, nothing else. So in this paper I'm going to present, they have used a wide varieties of data set, wide range, like different sizes, small, medium, and large. And also they have used two families of architecture, VIT, the transformer based and the CNN based architectures. So this paper only considers the isolated case and says that there is no feature reuse. There is no feature used by the transfer learning, but the benefit only due to over parameterization and weight statistics. And it also shows that it's like improving the speed of the training. So that is the conclusion of this particular paper. So here we'll move into the details of the paper I'm planning to present today. So here they have used like a range of data set. Here you can see there is a retinal fundus, high resolution diabetic retinopathy images. The size is like 3,662. And there is mammography, the size is like, here you can see the size is like increasing. And there are different classes, different data set, mammography, dermoscopy images, chest X-ray, and patches of HNE stained whole slide images of limb node section. And the tasks are also images. Yeah. So here the size of the data set is increasing. Yeah, the number of samples are increasing. So the tasks are also different. Here it's 5 classification. Here it's to detect the presence of masses. Here 9 class classification, different types of skin lesion, I think. And here 14 class classification. Here it's just cancerous or non-cancerous, 2 class classification. So in this work, as I mentioned, they have used small data set. You can consider this as a small data set, and then 3 medium data set and a large data set with like 327,680 samples, images. Yeah. Yeah. So here, in addition to the Inception and ResNet, which are like CNN based model, they are also using DIT and SWIN transformer models. DIT is like the data efficient image transformer by Facebook, and this is a SWIN transformer. So these two are the VIT based model, these two are the CNN based model, but in the related work I showed earlier, they only use the CNN based model. So here I have color coded red to green. So here this is red because this the DEIT model is a purely transformer model. It does not have any inductive bias. But with SWIN transformer, what they have done is they use the self-attention with hierarchical structure to embed some kind of inductive bias. And this CNN models always has this inductive bias. So here it's in an increasing range, like it's increasing the inductive bias from day to day. Like the model has a knowledge about what the image is like in terms of one inductive bias is locality, because in transformer we don't know what what region is close to each other, we have to give it as a positional encoding. But the CNN has that information embedded with it. So since this is a pure transformer, this doesn't have anything, but they're trying to embed with the attention, using attention some way.
So in that case, like if you think about the CNNs are the ones that have the two sides,
Yes.
that means like the locality and then the
Hierarchical structures, yeah. 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 So when we compare this with the previous related work, they only use the CNNs, and in this case, they are using VIT models too. So that is why I'm saying this as a isolated case, because they are only using large data set and only using the CNN based model and claiming that there is no feature use. So here it's initialization. Yeah, so the transfer learning benefits can come in two ways. One is like the feature reuse, like the features learned in the source domain is being used in the target domain. That is one advantage of using transfer learning. But the another possibility why transfer learning is working, because it's giving just a good initialization point. Instead of helping with the feature reuse, it's just giving a good initialization point so that the model is converged at a optimum point. So to isolate the contribution of this feature reuse and weight statistic, they are using three initialization method. First one is the random initialization, like randomly initialize the weights. Second is the weight statistic transfer. So as I mentioned earlier, like they're taking an ImageNet pre-trained model and taking the mean and standard deviation of those weights. And then from that normal distribution, we are sampling the weights. The third one is weight transfer. We are like directly using those weights for the next task. Yeah. So that is the methodology section, and we'll move into the results, like why transfer learning is working for medical images. So in this slide, we'll see when is transfer learning to medical domain is beneficial and how important is feature reuse. So there are 4 subplots. So this is for the DAT model, the data efficient image transformer, and this is Swin transformer, Inception version 3, ResNet 50. And the x-axis is the dataset size, y-axis is the distance from ImageNet. So from here, you can see Patch, Chameleon, and JXpert are like high in data size, and the distance from the source domain is also high. And for this Aptos is they're using FID score to measure the distance between the distribution of ImageNet and the distribution of the target.
distribution of weights, distribution of what?
Image distribution. No, directly the pixels and the image distribution.
Oh, I see.
Yeah, so here you can see this retinal fundus, mammography, and the skin lesions are like small data sets, and also closer. This one is the ISIC is closer to the source domain.
Wait. So the distance from ImageNet is on the data set?
No, they are calculating with the like using the FID matrix, I think. Freshet inception distance. I'm not sure what that means. Based on the images, you have the ImageNet data, like the images, and the
For the point, it is on the image, it's one independent, then it is the same, right?
Yeah, the distance is same, right? It's all.
So the location is information is on the size of
the information, the size of the is different. So the relative increase in the performance is the size. Okay. And the color is different, but you can see from y-axis it's always the same, the distance in the y-axis. So here it's always 160, 160, it's 160 and again 160. It's always the same. Yeah, it's dataset size, it's always the same. The location of these circles are always the same. The color and the size are varying depending on the performance. Okay. Yeah. So this
I have one question. So this FID score, like, isn't it dependent on the image size as well?
depend on the image size. I'm not sure. But
Uh,
the
all
image,
all these data sets of same image size or different
Uh,
image size?
obviously, to use the ImageNet pre-trained model, I think they have resized these images into 224 into 224 because that is how the ImageNet images are.
Yeah, okay. So when calculating the FID score also, they have used the same patches images or
Probably yes, I'm not sure. Those
Okay.
things were not mentioned, I think, but I think yeah.
The median is 96 by 96, right?
I think they can't hear because the mic is on this side. The patch chameleon is 96 into 96, right, Niroshan?
yeah, that's 96 into 96.
Yeah. Yeah. Yeah, so here you can see there are different sizes. The size of these circles are like indicating the relative increase in the performance of weight transfer over performance of random initialization. And the color of these circles are indicating the relative gain attributed to feature reuse. So what they are doing is they are calculating the relative increase in the performance of weight transfer and subtracting the relative increase in the performance with the stat transfer, like the weight statistic, like initializing with the mean and standard deviation. Yeah. So we'll look into the results. So what we can see is like in this CNN, these two are CNN, ResNet and Inception. The large data sets are not benefiting from the transfer learning because you can see the colors are like below 0.4. It's in blue, not in purple. So large data sets with CNNs are not benefiting. This is the isolated case which was analyzed in the related work I have presented. But here with a small data set, you can see there is a benefit because with the Aptos and DDSM, there is a kind of 0.6 to 0.8 range. And here, this ISIC dataset, the skin lesion dataset is the dataset closest to the closest to ImageNet. The distance from the ImageNet to the ISIC is the lowest. So since this dataset is closest to the ImageNet, it's like benefiting the most from the transfer learning, even with the CNN architecture. And the data size is also like sort of medium. Yeah. Yeah. And when you compare this VIT-based model, the DEIT, the data efficient image transformer, is always benefiting. It's always in purple color, like somewhere between 0.8 to 1. But this is also a VIT-based model swing transformer, but here you can see the patch chameleon or expert is not performing well. So the difference between these two are the inductive bias, because this DEIT model does not have any inductive bias, no inductive bias at all, but swing transformer was able to embed some amount of inductive bias by the self-attention and the hierarchical structure. So from this figure, what we can say is the smaller data sets are benefiting, and when the distance between the source domain is less, it's benefiting, and also when there is no inductive bias, the model is benefiting. So that is the conclusion we can come from this figure. Yeah. So in this slide, we'll see which layers benefit from feature reuse. So there are again 6 subplots, each for each data set. This is for Aptos, this is for the mammography, skin lesion, chest X-ray, and chameleon data set. And this gives you the average relative gain, average over the whole data set. So here the y-axis is the evaluation metrics. For different data set, they are using different evaluation metrics. For Aptos, it's kappa, and then AUC curve, recall, AUC curve, AUC curve. But always the range, the range of the evaluation metrics is 1 to 0, so they are taking the average over here. And W2 fraction is like what they do is they transfer the weights for the first n block and initialize the remaining m block with a stat transfer, which means the mean and standard deviation they calculate from the ImageNet model. So this W2 fraction is n over m. Yeah. So in these figures, what we can see is when the data set size is large, for example, the J expert or the chameleon, The CNN models, the brown or the orange curves, you can see those are like flat for the large data set, which means the CNN-based models are not benefiting most, and there is no feature reuse. So that is what indicated by these flat lines. But when it comes to small data set, there is a linear trend. Yeah, so it means that the CNN models are benefiting. I mean, CNN models are like reusing the features when the data set size is small. So when we look at this DIT model, which is in blue curve, sorry, here you can see there is a jump in early layers, and then from the later layers, it's going flat. So here also you can see there is a jump in the early layers, and then it's going flat. So this means that for a VAT-like model, I mean, for this DIT model, there is the early layers are benefiting from the transfer learning, but not the later layers. When you see the swing transformer, it exhibits the behavior of both CNN and DIT model, because here you can see DIT, because here you can see for large data set, it's flat, the purple color line, purple color curve. But for the small data set, it's again, there is a jump in the early layers and then it's going flat. So the swing transformers are like exhibiting behavior of CNN when the data set size is large, and exhibiting the behavior of DIT when the data set size is small. Okay. So in this slide, we'll see what properties of transfer learning are revealed via feature similarity. So here you can see, so these subplots are like, here you can see there are five columns for each data set and 2 rows. Yeah, first row is for the DEIT model and the second row is for the ResNet. So here higher similarity mean red color, and you have to like the higher similarity in the diagonal means the feature reuse is at optimum, because this is layer 1, this is layer 1, and this corresponds to the layer before and after fine tuning. Yeah. So here, so here this each plot indicates the layer wise feature similarity resulting from transfer learning before and after fine tuning. So this X is before fine tuning, this X is after fine tuning. So in this diagonal, if it is in red, that means in those layers the feature similarity is at optimum, which means the feature reuse at optimum. Yeah. So with the DIT model, what we can see is there is a maximum feature reuse in the early layers, but in the later layers, the feature reuse is like reducing. So as it's in, sort of in alignment with the previous observation, the early layers are benefiting most from the transfer learning. In the early layers, the feature similarity is high, and in the later layers, it's reducing. And with the ResNet, we can see that the feature similarity is high throughout the network. As we already observe here, the feature similarity is in the average relative gain. The feature similarity, like the performance gain is always consistent throughout the network. And here also we can see the feature similarity is consistent throughout the network, but in the last layer, there is a difference because the last layers and here the latter layers have to adapt for the new task. So in this slide, we'll see which transferred weight changes. In the previous slide, we saw the features, and in this slide, we'll see the weights. So they are doing a L2 distance between the initial weight of the network and weights after fine tuning. There are 4 columns like for each model, DEIT, swing transformer, inception, and ResNet. Here the y-axis for the mean L2 distance and the x-axis for the network depth. Here you can see 4 colors, green and green to red. So here the green color is corresponding to weight transfer, stat transfer ratio 0:14, which means there is no weight transfer, but all the layers are initialized with the stat transfer. And for the red color curve, you can see the weight transfer stat transfer ratio is 14:0, which means there is no stat transfer, but all the layers are initialized with the weight transfer. So the observation we can do over here is, you can see it's like going a flat line, which means the mean L2 distance between the weights before fine tuning and after fine tuning is always minimum, which means the weights are not changing by a lot. The similar observation can be done for the other networks also. Compared to the stat transfer, the stat transfer is around 2, and for weight transfer, it's around almost less than 1. And also you can see there is an inevitable jump in the early layers, or in like the first layer, or even in the middle. So they say, like the authors say, that this is inevitable because these are the layers which sees the image at the first. So here this first layer will encounter the image first. So those weight will anyways have to change. And here this is high because these are the scale changes from the convolutions, like the scale of the kernel changes from this point to this point. So this is the layers which encounters the scale changes. So the weights will anyways have to change. So that is why this jumps are there. So here also you can see the green curve is on top of red curve, which means that the stat transfer, after stat transfer, the weight changes by a lot. But according to the red curve, the weight transfer weights are not changing a lot even after fine tuning. Yeah. So in this slide, this slide is about what is the impact of transfer learning for different model capacities. So there are again 5 columns for each, like each column is for 5 different data set, and first row is for the ResNet and the second row is for the DEIT model. So the green curve is for the ResNet 18, the blue is for ResNet 50, and red is for ResNet 152. So here you can see, like, as the W2 fraction increases, the red curve is coming on the top, no matter like whatever the data set is, which means has the weight transfer ratios increasing. And if the model capacity is also increasing, then the model with the most capacity is like performing better. So that indicates that the model with the most capacity like performs better with the transfer learning. The same thing can be observed with the DEIT model also, the data efficient info image transformer. So the red curve is coming on top all the time. Finally, they also did an experiment on what is the impact of transfer learning on convergence speed. So it's monotonically increasing. So here you can see for the CNN, the inception of the ResNet, it's kind of a linear as the weight transfer fraction is increasing. As number of layers initialized with the weight transfer, the convergence speed is like increasing linearly. But with the DEIT model or the swing transformer, it's increasing up to a half region, like about 0.5, and then it's sort of like a flat region. The improving the speed is like diminishing, which means like has in line with the previous observation, the early layers are like benefiting from the transfer learning. So the early layers are benefiting from, like, the speed is also increasing when we replace those weights, but the later layers are not. Once again, finally, the contribution of this paper, like here you can see, I'm just re-summarizing the contributions of the paper. So this paper shows that the benefit of transfer learning increase with reduced data set, smaller distance between source and target, model with fewer inductive bias, and models with more capacity. The paper also shows that the benefit of transfer learning is correlates with feature reuse, not just the weight statistics. And it shows that there are feature independent benefits of pre-training, like the speed ups. Thank you.
Go back to that slide, the layers. Yeah.
Mm-hmm.
So this one is the early layers has to change.
The early layers means the first layer which encounters the image will see a different distribution than it learned earlier, because the image are natural images and this is the medical image. So the early layers, the first layer has to change, and also the layer which encounters the scale change has to change, but the It's always in the lower pattern.
In the last layer,
For DAT model, it does not matter the last. But for the CNNs, the weight transfer is consistently helping. But for the DAT model, it's helping up to some fraction, but then it's like a flat region. DAT is sufficient transformer based model. Any questions?
that happens when you use something like that. So the transfer learning, separate data set and then
I haven't
that
looked
is
into
basically,
that.
I think the difference is like in transfer learning, you use the cost function. The transfer learning, you don't use the labels
Yeah, without
and
labels.
it's just the representations.
There should be any work, but I haven't came across.